Okay, so we're at part 220. It's been a while since I've filmed. Today is May 29th, 2012 at 10:16 p.m. And now we're going to look at line 19a, Dynamical, System Rocket Speeds, Isotropy, Speed of Light, 5G Wow Seti. As you know, the last video was line 18, so now we're finally on line 19. Here's the alien radio signal, because we're going to be getting into a new math equation, which is 13111, and that's in this line here on the Wow signal. And then here's the actual radio signal, and there's the math equation there. So we divide all the numbers and it comes up with this answer here. So I Google this number here, plus I also Google the answer. So both are Google for the data for line 19, actually for every single line that I filmed. My little globe here that I got for Mother's Day is very handy for when I do my predictions and stuff, but right now it's getting in the way of my filming, so I'm going to move it over there. And I've got the fan on, so my papers are flying around in here. So hopefully it was over 30 degrees today here, so it's pretty hot. Humidex is almost up to 40. So Minkowski space, again, this is the keyword from Wiki. And so I Google a dynamical system rocket speeds on some statistical properties of dynamical systems, SMULM, proceedings of the fourth Berkeley synopsis. So this is just a Google search thing that comes up. So it says the greatest final velocity of the rocket was about 3.7 times the, and then it's got speed and dynamical system. It also talks about asymptomatic behavior. So basically that's what that's about. It looks like a Google book or something. So the next thing that came up was clock synchronization and isotropy of the one-way speed of light. The Doppler cancellation scheme was built into the data acquisition system. It talks about rockets, velocity, and propagation along fiber. Okay. Another thing that came up was Clifford M. Will, McDonald Center for the Space Sciences, Department of Physics. He's got, this was published in 1991, experimental tests of the isotropy of the speed of light using one-way propagation are analyzed using a test theory of special relativity. It is shown that when properly expressed in terms of measurable quantities, the results of such experiments are independent of the method of global synchronization of clocks. Experiments analyzed include a jet propulsion laboratory, time of flight measurement, a resonant two-photon absorption experiment, the Smithsonian Astrophysical Observatory, NASA 1976 rocket gravitational redshift experiment, and Mossbauer rotor experiments. If the characteristics anisotropy is proportional to AW, where W is the velocity of the Earth relative to the cosmic background radiation, the best bound on A from these experiments is that math equation, and that's from 1992. So this is the research information that's coming up in the video, and I'm just showing you my research. Whatever words and stuff come up, I videotape it, and then I figured I'd be done. I only got another 7 more lines to go, and then we're done with the actual signal. And then I'm going to have to do the cross-referencing to try to figure out what all these keywords mean. So May 14, 2012, this is when I was originally working on this about 2 weeks ago. And then I got engrossed in the Hurricane Beryl and severe weather predictions and stuff, and I've been busy doing that, and I've been busy working on some novels as well. Sorry, I'm rambling here. My thoughts. Looking at the data again, I'm kind of confused about how I was doing it before. I'd actually forgotten how I was doing the Google search. I figured I was just doing the last answer thing, and then I realized no, I was doing the actual numbers of the equation and then the answer, so hopefully I've done them all correctly. Not only did I Google the actual equation of numbers found in the Wow signal, I also Googled the answer to the equation. I think I forgot all about that before. The equation numbers bring up the keywords. The answers to the equations bring up the data to look at along the inventions and patents. So I would look for the keywords. I would pull out whatever keywords stand out with the equation numbers, and then I would take those words and look for data to explain to me what exactly it was. So the Google from line 19a from the data. On some statistical properties of dynamical systems. This is the key set of words that stand out to me. So that a large number of particles or constraints in a dynamical system is required. So then I look up the data results and I get energetic motion of n particles in constrained dynamical systems from IOP Science, IOP.org. And it's by Tei Konishi, energetic motion of n particles in constrained dynamical systems. This article has been, and then of course this is a paraphrase, particles near the ends of the chain have larger kinetic energies where n is the number of particles, mi is the mass of the nth particle, and there's some sort of equation there. Interesting that xi and yi they came up before that particular math equation. So I'm going to Google energetic motion of n particles to find out what comes up. This is another PDF file comes up. Energetic motion of n particles in constrained dynamical systems. This is from Tetsuro Konishi and Tatsuo Naginata, and it's a PDF. Anyways, it says, we propose a planar chain system, which is a simple mechanical system with a constraint. It is composed of n masses connected by n minus 1 light links. It can be considered as a model of a chain system. Example, a polymer in which each bond is replaced by a rigid link. The long time average of the kinetic energies of the masses in this model is numerically computed. It is found that the average kinetic energies of the masses are different, and masses near the ends of the chain have large energies. We derive an approximate expression for the average kinetic energy, which is in the qualitative agreement with the numerical results. There's their keywords there. It's 2009. So I'm going to Google N1 light links to find out what that is. I've got this graph here. Okay. It says the energy gap band for heavy holes is smaller than for light. Journal of Optics, volume 14. Sorry, I keep yawning. Semiconductor heterostructures and optimization of light trapping structures for efficient thin film solar cells. From all those people. There. Okay. So sub-wavelength photonic structures and nanoscale materials have the potential to greatly improve the efficiencies of solar cells by enabling maximum absorption of sunlight. Semiconductor heterostructures provide versatile opportunities for improving absorption of infrared radiation in photovoltaic devices, which accounts for half of the power in the solar spectrum. These ideas can be combined in quantum well solar cells and related structures in which sub-wavelength metal and dielectric scattering elements are integrated for light trapping. Measurements and simulations of GaAs solar cells with less than 1 micron of active material demonstrate the benefits of incorporating in GaAs quantum wells and quantum dots to improve their performance. Simulations that incorporate a realistic model of absorption in quantum wells show that the use of broadband photonic structures with such devices can substantially improve the benefit of incorporating heterostructures, enabling meaningful improvements in their performance. I apologize if I'm not saying the words right. That was published January 2012, so it's fairly new. So that's the end of that video. We'll go on to the next one.